Okay, let's try this. All right, welcome to Unit 3, Cryptography. All right, I got a note sheet for you about the basic ciphers we're going to talk about here on the first day. All right, so first of all, what's cryptography? Cryptography, it says here, I think you know what it means. It's like when we're talking about computers and encrypting information or files or any data you want to transmit from securely from one party to another. The messages and the kind of information we're going to be quote unquote sending this unit are about plain text messages, usually just like a string of capital letters, which makes it kind of simple. And that's enough to get going on at least the math behind how some of these more complicated actual, like real life computer ciphers actually can work. But of course, we got to start off at square one because this is the first time you probably ever talked about it. So anyway, get familiar with some of these terms. Today, all of the stuff we're going to be doing is from the For All Practical Purposes book, and you have section 17.4 is the only part that you've got scanned as a PDF in Schoology, and that's where it goes. And you'll see little page references as I go through this thing. I noticed when I had the word today here, I don't mean today like nowadays in the world of cipherology. No, I mean like today, as in this day of the unit in this class. The four we're going to talk about today are about those. So that's what that means. All right, so the first one is called the Caesar cipher. It's probably the most simple one you've ever heard about. You may have even thought about doing this on your own as a kid, maybe, because it's really simple. So basically, you take each letter of the alphabet and you shift it down the alphabet. So the one that I've got indicated here, and you can read about it, the one I've got indicated here, it's shifting every letter 3 letters to the left. So E gets encoded as a B. So what? And Caesar ciphers don't have to be exactly 3. They could be any value left or right up to the full length of the alphabet. So one way to do that is this one that I found in Wikipedia. It was very nicely illustrated. So one way to kind of show that quickly and line that all up is type the alphabet as regular and then show the alphabet below that shifted over 3 letters. And I think you can see why we're talking about a shift of 3 here. I took A and went boom, boom, boom over 3 letters, and that's where I dropped the A, and I started the alphabet there. And then notice this: the rest of the alphabet's going to wrap around like this. We call that a Caesar shift of -3. Then the other direction will be +3. So here's a original plain text message I was talking about. So if this was the original message, and this is actually from a movie, I pick up random quotes and I just insert things I think are funny into this class, and I corrected the grammar on the original movie quote. If you can tell me what movie that's from, you gain my respect. Okay, so in this message, all the original W's are going to get replaced by T's because under the W there's a T, and all the W's turns into T's, and notice the T's turn into Q's because under T there's a Q. Again, very simple cipher, and it's so simple. In fact, if you were given this message and you knew it was a Caesar cipher, you could probably, just by context of English language and trial and error, you could try to figure out where this came from and what letters might have been replaced. So it's very vulnerable to hacking, actually. All right, so I've got this reprinted up here. See if we can try figuring this out. So in these, let's see if I can do this. B's are going to be replaced by, because here's the letter B. B turns into Y. Oh, that's interesting. A is going to turn into X. B I already know is going to turn into Y. Y turns into V. I will preserve the space. Y I already know turns into V. O turns into L right below it. D turns into A. And A turns into X. Hopefully none of these things turn out to be obscenities, but I always worry about that. All right, so that's each one of these letters just replaced with the letter below it. Okay, then decrypt. So this is the message that you've been sent. You know this was the cipher used. All you do is simply look for these letters in the bottom row and go look at what's above them. So above the P is S. Above the L is, looking up here, is O. Above the Q is T, etc. Can I just do this quickly? Uh-oh, first mistake. Cross this out. I realized what I did when I made this. I made a mistake. Just give me a second. Oops, you'll figure out what I did if you go back and see what I accidentally did. Okay, so if it's an encrypted message, it should be found in the bottom row. So now I'm looking at this J and I see, okay, I know that's an encrypted letter, so that's a J from the bottom row. I look above it. So J came from M, L came from O, P came from, what did I mess up? Okay, it came from N, etc., and you're going to figure out that this spells this. Okay, I was just being silly right there. Okay, great. Okay, so in this particular system, you keep spaces where they are. Other people or other books where you see the Caesar cipher, sometimes they call the space a 27th letter. And there's other ciphers we're going to do today or even next time that do count spaces as part of the code to be encrypted. Of course, computers do way more fancy stuff and keep, of course, capital letters and numbers and spaces and punctuation, all that stuff different. But even for simple Caesar ciphers, you might see spaces involved, or replacing spaces with the letter X so that the person who's decrypting has to use their human context knowledge to figure out the language. Anyway, we're not going to spend a lot of time on Caesar cipher because it's so simple. You can make a wheel like this and make this so you can spin the middle part and have it line up with the outer part, and you can create the key that looks like my little double alphabet row here really quickly for any possible arrangement of the cipher. So they make those. You can print those off and make them. It's kind of fun. Okay, for many of the other ciphers we're going to use this unit, you have to understand this whole new wing of math called modular arithmetic. So we're just going to get into modular arithmetic for what we need to do for ciphering and cryptography, but there's a lot to modular arithmetic, and it's really, really fun, and it's used in lots of things. Okay, so basically what modular arithmetic is about, it just operates with integers, and it's about reducing integers to their remainders once you divide by a certain number. So here's a first example, and you could look on page 715 if you want a formal explanation of this, but it's really not that bad. So we talk about 3 mod 2, and this is short for the word modulo. 3 modulo 2 is like trying to figure out if I take 3 and divide it by 2, what's the remainder? 3 divided by 2 is, it's 1, remainder 1. And they write that out this way so you can see the multiplication. Yes, so you can write 3 as 1 times 2 plus 1. So 1 is the leftover part. 6 mod 2 is 0 because 6 divides evenly by 0. The remainder of 6 divided by 2 is there's no more. So the way they're writing it here is always like, whatever the quotient actually is, like the whole number part of a mixed number. You can think about that way. Is kind of irrelevant. We don't really care how big this first number is. Notice this second number is whatever we're asking to mod by, and then the last number is really what we care about. It's like the remainder part. And this is really useful for lots of things in real life, figuring out remainders. Like if you wanted to know what day of the week is it, 37 days from now, well, I don't really care about 35 of those days. I only care about the last 2 because every 7 days I repeat the week, right? I go through the week again. I really just care about the remainder. So things like that. Sometimes it's called clock face algebra because if you talk about things mod 12, it's like, okay, in 50 hours, what time is it going to be? Well, subtract a bunch of multiples of 12 because we know every time we go 12 hours, the clock just spins around and we get back to where we started. So I just really care about the part that's after the multiples of 12. So here's a bunch of examples if you want to see that. All right, and we can do this on the calculator. 14 mod 3, let me show you. The first way you might think to do this, and it does get easier, but if we took like 14, that didn't work. 14 divided by 3, I get, oh yeah, I probably want that as a decimal. 14 divided by 3 is 4 point something, so 4 times 3 plus something is going to give me my 14. Well, I can tell that that's supposed to be 4 times 3 plus 2. So it's 2 that's going to be the leftover part there. Okay, you can rewind that, see if you want. We do things like this too. You might see like more complicated, this is much more complicated things in a mod question. 72 plus 15 mod 7. So because of the parentheses, yeah, you do 72 plus 15 and then mod that 7. So if I divide that by 7, I notice it's 12 plus some junk. Well, 12 times 7 is 84. So the junk I have to add on to 84 to get 87 is going to be 3. So I have to add 3 on. So I just found out that the part that's the remainder is 3. And again, I don't care about anything else. I just care about the remainder. Sometimes you might see this triple equals sign. We're going to use 2 different books during this unit. And sometimes it's the double equals and sometimes it's the triple equals. And they refer to that, or they read that as congruent. So you'd say 14, the way to read this statement is 14 is congruent to 2 mod 3. Or 14 mod 3 is congruent to 2. I've heard it that way too. Think about this. If we're going to do a bunch of things in mod n, what should be the largest answer you ever get when you mod something n? So in other words, if I take any number mod 3, what are the possible answers I could ever get? Well, think about all the remainders you could get when you're dividing things by 3. Things could either divide evenly by 3, in which case the answer mod 3 would be 0. Things could be 1 more than a multiple of 3, in which case the answer would be 1. Things could be 2 more than things could be 2 more than a multiple of 3, in which case the mod would be 2. And then the only other possibility is if you thought about being 3 more than a multiple of 3, well, you're back to a multiple of 3, and the answer would be 0 again. So really, things could be when you're modding things n, you could get 0, you could get 1, you could get 2, you could get all the numbers up to n minus 1, but you can't get any bigger than that. So sometimes actually they refer to this whole set of numbers, the set of numbers from 0 up to that n minus 1, as the set of numbers of integers modulo n. You see this is z symbol, like the symbol for integers, with a subscript n underneath it. Okay, I was doing the kind of silly way in the calculator a minute ago, but if I really want to do 14 mod 3 the slick way, there is actually a mod function on the calculator which you would much rather do rather than what I've been doing there. So I was trying to do 14 mod 3 earlier, and in my notes here I'm saying if you go, menu 285, let's walk through that. Menu 2 for number, and under there number tools 8, and under there 5 for mod. That's almost more clicks than just typing mod. But then after that, if I want to do 14 mod 3, I put this within the mod calculation and just does that. I could also do, I think I could even do stuff like this. That last one we did was 72 plus 15. I can put that expression in there. Oh, I might want to do another set of parentheses. Comma, what was it, 7? Yeah, and it just tells me that it's 3. So that's a whole lot fancier than the way we did it before. So what's 9 times 3 mod 4? 9 times 3 mod 4. I mean, really, I could go 9 times 3 and go, okay, 9 times 3, and that's 27. Sorry, that's silly. 9 times 3 is 27. I could go mod 27, comma 4, and it'll just tell me. The remainder when I divide 27 by 4 is 3. 37 squared mod 17. That's pretty crazy. 37 squared. And I want to mod that. You could go mod ants. What was it supposed to mod? Mod 17, and it'll tell me it's 9. So that's really nice. These are very high-powered calculators, and it'll do that stuff. But it says down here, but the calculator has its limits. Sorry, that's kind of cut off. We'll talk about that later. The calculator will put up with really large numbers, but there's a certain part where the calculator's like, forget you, I'm not doing a mod that big. And there's a workaround we're going to learn in a few classes. Okay, now we've got some mod stuff under our belts. You'll see why it's useful when we start to do the decimation cipher. So in the Caesar cipher, we were basically, it's like we were replacing all the numbers with letters, and then we were adding. I mean, if you imagine replacing all the numbers with letters, we didn't actually do that, but if you could imagine that now, this is a pretty simple thing to think about. We were just adding numbers, so like that's why the E turned into B, because it was like we were subtracting 3. That's another reason why we would call that the subtract 3 kind of Caesar cipher. This one is about, and we really have to think about numbers this time, instead of adding or subtracting and doing kind of a simple shift that way, we're going to be multiplying. So we would take some letter in here, multiply that number by a given, crypto number we're going to decide on, like, before it was a shift of 3. Well, here we're going to multiply by this number we're going to call K. But if you multiply, 18 by some number, very quickly you're going to go beyond 25. So we don't care about, we really don't want numbers bigger than 25. We just really want to know if we kept cycling that around like a clock face or like, days of the week or something like that, we could mod that number, mod 26, and we'll always get a number between 0 and 25, like we were just talking about. So we're going to do multiplication to take starting letter, to send it somewhere else in the coded message. But then we mod 26 to bring it back into here. And the cool thing is, each letter, as you do that, and if you pick K correctly, each letter as you do that is going to turn into a different unique letter. And it's always going to be able to trace back to where it came from. As long as we pick an odd, with mod 26 here, we have to pick any odd integer other than 1 or 13. And we will talk about why it can't be those later. See you in part 2.